for the final part in our third video series on homework review of chapter 7.3, applications of the dot product. Let's jump straight into it. So, question 6, we're leaving where we left off. Factory worker pushes a package along a broken conveyor belt from -40 to 40 with a 50 Newton force at an angle, a 30-degree angle to the conveyor belt. How much mechanical work is done if the units of the conveyor belt are in meters? Okay. So, this problem, in my opinion, is most readily solved with the geometric dot product. And I will show you an illustrated diagram as to why I think that. So we have a 50 Newton force. At an angle of 30 degrees to the horizontal. And the displacement is from -4 to 4. All right. The formula for work done in the geometric sense would be work is equal to F dot S, magnitude of F, magnitude of S, cosine the angle between those two vectors. Okay, we know what the magnitude of the force is. That's 50 newtons. Now, the magnitude of the displacement is going to come from the formula for the distance between 2 points. So that's going to be the y2 minus y1 squared plus x2 minus x1 squared. Okay. And this would be equal to 0 minus 0 squared plus 4 minus -4 squared. Which is so get 8 meters, and cosine is 30 degrees. So it's 50 times 8, cosine of 30, we get 346.41 joules. Now, just one note. I used the distance between two formulas here, the distance between 2 points formula here, but you could have intuitively guessed that the distance was going to be 8 meters. However, if you could not just use your intuition for this example, and the points were not collinear, then you would have to use this formula to get a better view of what the distance actually is. And then you can plug it into your work formula. Okay, so this formula applies in the more general cases, even though, yes, you probably could have easily saw from the problem that the distance is 8 meters. Good. Question 8. All right, I am not an artist. I just want to give a disclaimer for that before I start this problem. It looks like a physics word problem. Justin applies a force at 20 degrees to the horizontal to move a football tackling dummy 8 meters horizontally. He does 150 joules of mechanical work. What is the magnitude of the force? So this is my training dummy. And Justin's applying a force. We can call it F. Justin. J for short. And we don't know what that is, but we at least know its direction is 20 degrees to the horizontal. Okay. And the distance this dummy moves, S, magnitude of S, is 8 meters. And we're asked to find the magnitude of the force. Again, this problem is easily solved by using the geometric dot product formula for work. So F dot S, magnitude of F, magnitude of S, I'm guessing vector symbol there, cosine of theta, work. And we know the work done is 150 joules equals the magnitude of F. We know what S is, that's just 8. Cosine of 20 degrees. So then the magnitude of F, isolating for that variable, will lead to it being 158 cosine 20 degrees. Which is 19.95 newtons. All right, perfect. Moving on to question 9. Determine the angles of triangle ABC for A 5, 1, B 4, -7, and C -1, 8, -1, -8. All right, so let's draw our Cartesian grid. Let's get some points down. So 5, 1, 1, 2, 3, 4, 5, 1. A is right here. Okay. B 4, -7, 4, then 1, 2, 3, 4, 5, 6, 7. So that point will be here-ish, B. And we have the point C, -1, -8. -1's here, and then 1 down again. All right. Let's form the triangle. And now it's asking us to determine the angles of this triangle. So what's one way we know how to determine angles? It's using the equivalence between the geometric and Cartesian dot product. That's formula 2, which is right here. Okay, so we're going to use that formula quite rigorously in this problem. It'll be the workhorse of this problem, actually. So we need some side lengths, though, definitely, to solve this problem, because so we're going to need the side lengths. I'm going to calculate AC, AB, and BC, and I'll make that choice clear why later. AC, AB, and BC. So AC, so we're going to have -1, -5, -8, -1. Remember, I'm subtracting the CX coordinates from the AX coordinates, the CY coordinates from the AY coordinates. You're always subtracting coordinate points in the reverse order of how the vector is labeled. So we have -1, -5, -8, -1. Yep. You get -6, -8, -1, -9. Okay. AB, we're going to do 4 - 5, and then -7 - 1, 4 - 5, -1, and then -7 - 1, -8. Okay. And then BC, we have, just want to see, 4 minus 5, negative 7 minus 1. Yep, seems correct. And for BC, we have negative 1 minus 4 and negative 8 minus negative 7. Negative 1 minus 4, negative 5, negative 8 minus negative 7, we have negative 1. Perfect. And the angles we're after are the following: theta 1, theta 2, and theta 3. Okay, so let's calculate theta 1 first. So theta 1, remember to use the equivalence between the geometric and Cartesian dot products, or even the dot product as a whole. We need vectors to be tail to tail, right? So I'm going to use AC and B, and AC and AB here. All right, so cosine of theta 1 is going to be equal to AC dot AB over the magnitude of AC, the magnitude of AB. I guess we'll calculate the magnitudes here as well. So the magnitude will be square root plus 9, square root of 117 here, square root of 65. I'm just squaring each component and then putting it under the square root. It's the Pythagorean theorem. 5 squared plus 1 squared, square root 26. Excuse me. All right. That'll make our life a lot easier in this calculations. So then we have cosine of theta 1, AC dot AB. That's negative 6 times negative 1 plus negative 9 times negative 8. 78 over square root of 117, square root of 65. So theta 1 is then equal to cosine inverse of 78 over square root of 117 times square root of 117 times square root of 65. 26.56 degrees. I'm going to calculate theta 2 next. My choice here is, I'm making this choice in particular because the dot product won't allow me to calculate theta 3 because AB and BC lie tip to tail and not tail to tail. At least head to head, we can maneuver them as position vectors in a way to apply the dot product. So I'm going to calculate theta 2 here. Cosine of theta 2. Because remember, the dot product always wants vectors to be tail to tail before it can be applied. Cosine of theta 2. That's going to be AC and BC. AC dot BC, magnitude of AC, magnitude of BC, cosine of theta 2, so AC dot BC, that's negative 6 times negative 5, plus negative 9 times negative 6 times negative 5, 6 times negative 5, plus negative 9 times negative 1, 39, or the square root of 117 times square root of 26. So theta 2 is going to be cosine inverse of that ratio. Cosine inverse of 39 divided by square root of 117 times square root of 26. 45 degrees. Okay, perfect. Now, something strategic we can do, because mathematicians are always lazy. We can use the theorem on the sum of interior angles of a triangle formula. So we know that the sum of all interior angles of a triangle add up to 180. So we know that theta 1 plus theta 2 plus theta 3 equals 180 degrees. Thus, theta 3 would just be 180 degrees minus theta 1 minus theta 2. Beautiful. I guess you could probably best to do it like this. Okay. So then theta 3 is going to be equal to 180 degrees minus 26.56 plus 45. Oh. So 26.56. And we get 108.4 degrees. That is theta 3. That solves it. So just be careful on which vectors you can apply the dot product with. They have to be tail to tail. And that's one note. So tail to tail for the dot product. The other note being, anytime you're asked to find angles in this entire unit, and even probably most of next unit, you're using the dot product. Just drill that into your head. Anytime you're asked for an angle, just use the dot product. That's where your mind should go immediately. Using the second formula presented, the equivalence between the Cartesian and geometric dot products to find the angle. Okay, question 10. So consider the parallelogram with vertices at 0. Okay, so find the angles at which the diagonals of the parallelogram intersect. So we have the point 0, 0. That's 1 point. 3, 0. 1, 2, 3. 5, 3. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3. So right here. And 2, 3. 1, 2, 3. That's how the parallelogram looks. So we can start labeling some sides here, some angles. So let's call this point A. Actually, this will be point A. So that's 2, 3. This will be B. This point is 5, 3. C, 0, 0. And then the final point D, which will be 3, 0. Okay. And it's asking us to find diagonals of the find the angles at which the diagonals of the parallelogram intersect. So these will be the diagonals. It'll be A to D and C to B. So immediately, if I'm asked to find angles, I know I'm going to have to use the dot product, inevitably, and somewhere in the calculation. So A to D, let's calculate that side length. It's going to be 3 minus 2, 0 minus 3, 1, negative 3. Okay. A to D, 3 minus 0, 3 minus 2, 0 minus 3, 0. Yep. And then CB. That's going to be, make sure it's 0, 0, not 10, 0. So that's 5 minus 0, 3 minus 0, 5, 3. Okay. And now I can just find the angle. It's using formula 2 again. So cosine of theta is going to be equal to Cartesian dot product of AD dot CB over magnitude of AD magnitude of CB, and cosine of theta becomes AD dot CB, so 1 times 5, so write it out fully, 1 times 5 plus negative 3 times 3. Oh. The magnitudes can be square root of 1 squared plus negative 3 squared. And the other guy, we have 5 squared plus 3 squared cosine theta of 1 times 5 plus negative 3 times 3. It's negative 4 over square root of 1 squared plus negative 3 squared. It's 10 square root of 10. And square root of 5 squared plus 3 squared, square root of 34. Square root of 34, yeah. Okay, so then theta is going to be cosine inverse of that. So cosine inverse of negative 4, we can expect our angle to be obtuse. Cosine inverse of negative 4 over square root of 10 times square root of 34. And we get 102.5. 2 degrees. All right. And I guess I should label the angle we're finding. That would be the theta right here. I forgot to label that. Okay, good. Perfect. That completes this section. So important to remember that there's 2 formulas for the dot product which keep appearing over and over again, the Cartesian and the geometric. Knowing which one to use for the work applications is important. Knowing that if you equate them, you can find an angle between vectors. And then vector projection is kind of like its own separate application, but not really. There's this formula that solves it for you, and it gives you magnitude and direction of the projection. All right, perfect. And also, I guess, one last fact. The dot product between any two vectors always returns a scalar, not a vector. It's a scalar. All right, well, thank you, everyone. That concludes this section 7.3. I will see you all for section 7.4 soon. Have a great day.